Okay, here we go. Hi, everybody. With 2 lectures left, I get to talk about Stokes' theorem, which is actually often better than what I've often done because sometimes I've had to do it right in the last lecture. And so I'll be able to talk in some depth about it and actually go through the proof, at least outline the proof of this whole thing. Today we will talk about the Stokes' theorem, the divergence theorem, and the fundamental theorem of calculus. So let me just state these theorems first. They're all in one place because they all play the same role. They play the same role. So the fundamental theorem of calculus, which we learned in 21b, is that the integral from one point to another, from one end of an interval to another, of the derivative of a function is equal to the function evaluated at the upper bound of that interval minus the function evaluated at the lower bound. Whew. Allergy season, hardcore. So we learned that, and then we learned Green's theorem just in the last week, and we learned 2 parts to Green's theorem, and I'm going to write both parts down. Of course, I'm going to deal with a badly erased board, so I'll work with this board. Here we go. Green's theorem says the integral over the domain of the divergence of a function, and this function is, say, a function of x and y of 2 variables. It's a vector-valued function of 2 variables, integrated with respect to the area element on that domain, is equal to the integral over the boundary of the domain D of f of the location along the boundary dotted into n hat ds. It's a line integral. So this is the flux through the boundary, and this is the divergence. And you don't have to put the x and y here if you don't want to put it there, but just to emphasize, it's a function of 2 variables. So this is Green's theorem flux form. We, in this class, had to put a bunch of things together, right? You knew what an integral was, but I had to define for you the double integral. We knew we had to set up the notion of a line integral. We had to talk about normal vectors. We had to talk about vector fields. And we had to talk about this new operation, which is the divergence. Then we also wrote down Green's theorem circulation form. Okay? And that is the integral over the domain of the curl of f, the k hat component of the curl of f, integrated with respect to the area element, is equal to the integral over the boundary of the domain D of the circulation, f dot t hat ds. Okay? We noted that what we mean here is the net counterclockwise circulation if we use the right-hand rule associated with this. And I've always written it as curl of f dot k hat dA. Okay? Those are the basic theorems that we've learned thus far. The divergence theorem now is simply the 3-dimensional generalization of Green's theorem. The divergence theorem is the following. The integral over the domain which is in R3. This domain was in R2. It was a piece of a 2-dimensional domain. This is now a volume, okay? The integral over the domain in R3 of the divergence of a vector field f integrated with respect to, well, it's a triple integral. It's integrated with respect to the volume element of that domain. And now you should be able to just make a plausibility argument here and say, look, this derivative effectively canceled with one of the integrals, okay? And I got one less integral on the right-hand side. And that's the same thing that's going to happen over here. This derivative is going to cancel with one of these integrals, and I'm going to go over a surface. So I'm going to call sigma is a surface which equals the boundary of the domain. This should make sense to you, and on Friday I will bring my bubbles in, the bubbles that we'll make bubbles with, and play a little bit. But if you take a domain, a closed domain, there is some surface that bounds that domain, right? That's how we make boundaries. And that's why I kind of had to make the distinction about the normal vector and the tangent vector. These are all closed curves. I emphasized that these were closed curves, okay? So this is an integral over surface, which is the boundary of the domain. And you don't have to do this, but it's okay to put a little circle over there to emphasize that this is a closed surface. Because to bound a volume, you must have a closed surface. And then what do we have here? Well, we have the F vector dot, well, what could it be? It's the normal vector, and it's the surface area element, which is what we just learned. We learned about the normal vector to a surface, and we learned about d sigma. This theorem is actually very straightforward to prove. Just as we proved Green's theorem, the flux form of Green's theorem, in a pretty straightforward manner, it's simply an application of Fubini's theorem. Okay? It's simply an application of Fubini's theorem. So if you were to do it on simple cubes, it kind of pops out very easily. And then you can make the argument that you could piece together more complicated domains by piecing together cubes or rectangular prisms. So that's the divergence theorem. Stokes' theorem is the generalization of the circulation form of Green's theorem. But it's a little different, okay? So Stokes' theorem is a little more subtle, okay? I put them side by side to emphasize the analogy. But actually, with divergence theorem, to get divergence theorem from Green's theorem, we recognized that we were going to do volume integrals. In fact, for Stokes' theorem, we're not going to do volume integrals. Our left-hand side will still be surface integrals. So I want you to think of Green's theorem over here and k hat dot dA, just for a moment. We're integrating in the plane, in the xy plane. So k hat is the natural normal vector to the xy plane. This is actually the unit normal. And in the xy plane, d sigma, the surface area element, is simply dA, because it's not a curved plane. So you can use dx dy or rd theta or what have you. So my point is, Green's theorem, this left-hand side, actually carries over in the following way to Stokes' theorem. The double integral, now the domain is a surface. So I'm going to write this over a surface which is contained in R3. This is a surface inside of R3. So this is two-dimensional, 2D. Okay? The integral over some surface, this is sigma for surface, of the curl of f dot n hat d sigma. So instead of dA, I'm doing d sigma now. So we're imagining a complicated surface equals the integral over the boundary of the surface of f dot t hat ds. Okay, so again, pause. First, I'm gonna flesh this thing out in total detail in a moment, okay? But I want you to just take it all in. All of these theorems are an expression of the fundamental theorem of calculus. The fundamental theorem of calculus is the relationship between integrals and derivatives, okay? And these theorems, Stokes and divergence, generalize those relationships, okay? As you can see, the left-hand side, we have an integral of a derivative, and they effectively cancel, so that we have the function evaluated on the boundaries of the domain. The function whose derivative you're taking is evaluated on the boundaries of the domain. And so too here, an integral and a derivative effectively annihilate one another, they cancel each other, and the function is evaluated on the boundary of the domain D. With Stokes, you have, it's very similar to Green's theorem, where you have the flux. This is the flux, because it's the normal component of a vector field. the flux of the curl of a function, the flux of the curl, which is interesting. And one derivative cancels with one integral, and so you're left with one integral. This becomes a line integral, and it equals the circulation around the boundary of sigma. So now let me draw a couple of pictures. I have to draw some pictures right now, okay? So I'm going to draw a picture over there. Visualize, if you will, a sock. Okay? Let's work with a sock. Okay? The sock is the bubble before the loop has closed of the bubble. So I want you to imagine a sock. And here I have some sort of opening to the sock, and I have some sort of threads. This is a badly drawn sock. Draw, well, I want to get some more curvature to this whole thing. So we know we can weave this sock in a certain way where we have rings of thread that go around, and then lines of thread that go along. This object is the surface that I'm talking about. Sigma is this surface right here. Okay? What is the boundary of this surface? What is the boundary of this surface? Well, you'll notice that I didn't call this a closed surface. This is possibly an open surface. This is an open surface. And as you can see, here is an open surface, like a sock is an open surface. Okay? There is no way to determine what is inside and what is outside. If you were to pour sand in a sock, it would flow out of the sock. Right? Now, if you had pinched that top, closed it off, then you've created a closed surface. Okay? And so that's like now taking the bubble, you create this bubble. I got this big hoop in my mind that I create bubbles with when I'm with children. And you create this bubble, and then you pinch it off by closing the hoop. And then the bubble floats away. That's a closed surface. Okay? What is the boundary of sigma? The boundary of sigma is simply this curve that lives down here. Is this curve right over here. That's the boundary of sigma. That's the boundary of sigma. So this is the geometry that you should be thinking about when you think about Stokes' theorem. And there are some very interesting consequences to Stokes' theorem. Consequences. One, for any fixed curve in R3, so let's imagine a fixed curve in R3, and let's call that C. Okay? There's a fixed curve in R3 right there. C is the boundary of infinitely many surfaces. C is the boundary of infinitely many surfaces. How do you think about this? Think about bubbles again. Think about taking a little wire hoop and dipping it into the bubble solution, and you let it go. And now you're looking at a wire hoop with a soap film in the middle. That wire hoop is C. Okay? The soap film is one surface. It ends at C. Now, blow on that surface. Any of those deformations of that soap film also have the same boundary C because it's still connected to that wire hoop. And how many possible surfaces are there? Well, as many as you want, right? Anything that ends at that surface. So you blow the bubble really big or small, it goes wide, whatever it does. As long as it remains connected to that hoop is the boundary of C. So something interesting about Stokes' theorem this implies, therefore, the integral over a surface, which I'll call surface 0, some surface, that's the flat surface, of the curl of f dot n hat d sigma is equal to the integral around sigma 1 of the curl of f dot n hat d sigma. For any sigma 1, which shares the boundary, which shares a boundary, its boundary, not a boundary, its boundary with sigma 0. So if the two surfaces have the same boundary, it doesn't matter. The integral, the flux of the curl through those surfaces will be the same. That's kind of an interesting fact. Okay, what does that mean effectively for you? Well, it means that if I give you, say on an exam, maybe, a complicated surface over which to calculate the flux of the curl, you would say, wait a minute. I know that he told me this, so if I find a simpler surface that has the same boundary, it's easier to do this integral. Okay? What's the classic example of this problem, of exploiting this simplicity? Well, what if I had made the surface be a hemisphere? Okay, so this is upper hemisphere, e.g. Upper hemisphere. The upper hemisphere. Okay? Well, the boundary to this hemisphere is the equator. It's this curve right here. So if I were to say, hey, this is the northern hemisphere. Now, if I were to say, hey, this is sigma 0, which is the upper hemisphere right there. And this is the boundary of sigma 0, which is the equator right there. And I give you some vector field, which you have to, and I say compute that integral on the left-hand side. Well, this disk down here shares the same boundary as sigma 0. So this disk down here, sigma 1, has the same boundary. This is the disk. So you just take an upper hemisphere and you take that disk at the bottom. They have the same boundary. In other words, you can deform the disk into the hemisphere. And I actually ask you to think about blowing bubbles. I think for me, it's always been the most intuitive way to think about it. Okay? So that's consequence number 1, which is an important consequence of this, of Stokes' theorem. What about consequence number 2? Consequence number 2. Closed surfaces. So now imagine the bubble again. And I've created a bubble with a hoop. But I'm going to close that surface. So the act of closing the surface, the way you should think about it is you are shrinking the curve C, which is equal to the boundary of the surface. What are you doing? You're shrinking. I do this with 2 bamboo rods and some string, right? And I open it up, and then I close those 2 bamboo rods so that string hoop closes. I'm shrinking the curve, which is the boundary to the surface, to the point where it goes to 0. Okay? Or another way of saying it is you're cinching up the end of a sack of some sort. Okay? So the boundary, that boundary goes to 0. Therefore, the boundary of sigma goes to 0. Therefore, the right-hand side of Stokes' theorem is equal to 0. For a closed surface, A closed surface has no boundary. Right? This was the argument, well, it was never really an argument, but this is the apocryphal argument of the time of the explorers, right? Will we go over the edge of the world? Well, if it was a disk, we would. But everybody, since time immemorial, knew that the world was a sphere, right? And we know that there's no way to go over the edge of a sphere because you just keep going around. There's no boundary to the sphere, okay? So the right-hand side is 0. And this gives a very interesting consequence to Stokes' theorem, which is the following. For any differentiable vector field, it has to be differentiable, okay? Which means that the curl has to exist. For any differentiable vector field, f vector, the integral around a closed surface, this is a closed surface now, so close the surface of the curl of f dot n hat d sigma, that's equal to 0. Every vector field, this is true. If you integrate the curl, the flux of the curl, that's what this is, the flux of the curl through a closed surface, it's equal to 0. And this is for any closed surface for any vector field. For any closed surface for any vector field. Now, it's worth just pausing and looking at the divergence theorem here, okay? The divergence theorem. And notice that this looks like the right-hand side of the divergence theorem, right? Where this f is the curl of that f. Okay, so let's think of divergence theorem. I'll have to write it again. Let's say the divergence theorem, let curl of f equal g. Let me just call that g, okay? And so the right-hand side of divergence theorem, so the divergence theorem gives me this. The right-hand side is the integral of g dot n hat d sigma, and the left-hand side is the integral over the domain of the divergence of g d volume, the volume integral of the divergence of g. So I just rewrote that with a g, another vector field, and it happens to be g is the curl of f. Okay? And this is the boundary of d. Sigma is equal to the boundary of d. Ay, ay, ay. Sigma is equal to the boundary of the domain D. And it's closed, right? Because the boundary of a volume must be closed. This right-hand side is 0 for all domains D and all vector fields G. But that's another way of saying that this left-hand side is 0 for all domains D and all vector fields G, which means that for all vector fields G, the divergence of G, so for all vector fields G, which are the curl of another vector field, the divergence of G is equal to 0, which says that the divergence of the curl is equal to 0. Okay? So that's another way of thinking about it. The divergence of the curl equals 0 implies this integral inequality. Sorry, this integral equality, I apologize. Okay? That's Stokes' theorem. Now, I have to make a couple of notes about Stokes' theorem. Okay? And the note is the following. We have to think about now what we mean by what do I mean by this Stokes' theorem? I know what I mean by n hat, I think, but what do I mean by t hat? So remember, over here in Green's theorem, this was k hat. This was out of the board. Okay? But n hat over here was out of a closed volume. That's no problem. I get it. What's a closed volume, what's out, what's in, not a problem, right? But this is in general an open surface, and so it doesn't close a volume. So like I said, with a sock, there's no obvious out and in. There's no obvious out and in. So I have to tell you what out and in are right now. Okay, and so I'm going to tell you what out and in are right now. So we need to get basically, it's getting the relative direction of n hat and t hat right. Okay? And let me show you how it works. Okay? quick commentary. The beauty of Stokes' theorem, by saying you go from the upper hemisphere to the plane, is that basically this argument means that Stokes' theorem can reduce to Green's theorem when you have a simple curve in the xy plane. Stokes' theorem reduces to Green's theorem. Okay? Now, they better both be correct, or else they're not theorems. So let's say they're both correct. Okay? And let's look at Green's theorem right now. Let's look at Green's theorem. What I want to do is I'm going to draw this axis over here. This is going to be the z-axis. This is going to be y. And this is going to be x. And I am going to draw a domain in the xy plane where I'm going to use Green's theorem for a second, okay? So let's imagine this domain in the xy plane. So this is supposed to be only in the xy plane. It doesn't look great. I admit it. It doesn't look very good, does it? It looks like it comes out of the plane there. How's that? That looks like it's staying in the plane, sort of thing. Okay? Or else my perspectives are all wrong. Okay? So that's a domain in the xy plane. Okay? Now, Green's theorem says the following. Well, let's look at the circulation form of Green's theorem, because I want to work it into the form of Stokes' theorem. It says the double integral over this domain D of the curl of a vector field dotted into k hat dA is equal to the integral over the boundary of the domain D, which is closed, of f dot t hat ds. This is counterclockwise. So now we've already established the correct signs of everything here, okay? So what are the correct signs? T hat are the unit vectors going along the curve this way. That's counterclockwise, right? You start on the positive x direction, you go toward the positive y, and you come around, okay? These are t hats. So that's t hat. K hat is k hat. It's up. It's in the z direction. So if you can bold that up, that's k hat. Okay? So that's Green's theorem. It says if you do the line integral of the vector field around here, it's like taking the dot product of the curl with this k hat, integrating it over the domain. That's Green's theorem. It had better be consistent with Stokes' theorem. And the answer is, well, of course it is. In fact, I'm going to use Green's theorem to prove Stokes' theorem. Okay, and here we go. What am I going to do? Well, let's fix that boundary for a second. Let's fix that boundary. Okay? And let's use the fact that multiple surfaces which share the same boundary, right, will have the same value of, for Stokes' theorem. Okay? So I'm going to deform. I'm going to take that axis. Here's y. Here's z. And here's x. I'm going to try to maintain that wiggly boundary, which I couldn't even do right the first time. Okay? Hey. It's pretty good. You know, I'm not proud of myself when I get the math right. That's obvious, right? I better get the math right. It's when I get the pictures right that I'm very proud of myself, because I can't draw. So it's just like you got lucky. You guys remember the helix incident of mid-quarter? The helix incident of mid-quarter shall never be forgotten. It was an embarrassment. Okay, that's t hat. Now what am I going to do? I'm going to blow a bubble. I'm going to deform this surface up. Okay? So allow me to deform this surface up. Okay, if you don't mind, you see the perspective there? Okay, sort of thing. I'm trying to do a perspective there. What happens to that k hat? In blowing that surface up, the k hat deforms to out here, right? Now, it's not outward normal. It's not an outward normal. Because if it was pointing in the opposite direction, well, you could say it's pointing into the surface, but what does it mean to be into the surface? It's an open surface. Right? You can climb in and out without a problem. There's no surface to keep you from there. So it goes this way, okay? So we need a new way to think about the geometry here. We need a new way to think about the geometry here to get this right, okay? And the answer is very, very straightforward if you look locally at the boundary here, okay? Locally at the boundary, let's look. I want to take a piece of the sock, right? The one that's up your ankle, at the top of your ankle. And right there, there's the curve, which is the thread that goes around your ankle. Okay? And here's the curve, which is the thread that's right beside it. This is not sock. Not sock. This is sock. Sock. Spelling is not a forte either. And the threads, therefore, go this way. Okay? The threads go this way into the sock, right? These are the threads. This is one of the threads. This is another one of the threads. This is a third one of the threads. I'm sort of trying to weave it, okay? Those threads that are going in. These are the in directions. So this is in. Okay? Notice that in came from the in, right? That came from a thread that might have been lying here and then turned up like that. That was in on a flat plane. That made sense, and then it turned up. So this is in, and this is tangent. And so we maintain this order of cross product. To maintain the relative directions, we say the following. For Stokes' theorem to work, we have to choose a relative direction, coming over here, coming over here, coming over here, of this normal vector and this tangent vector. And the relative direction can be read this way. There's one unique fixed in. There is in. We know which way the in vector is. That's the thread that goes from the boundary in. So we have the following relative directions. T hat is this way, in hat is this way, T hat cross in hat is n hat. N hat is equal to T hat cross in hat. In other words, everybody, there's no absolute counterclockwise in 3 dimensions. Take a clock. You look at it this way. Counterclockwise is this way, right? Now go behind the clock. Sorry, you take a clock, right? Counterclockwise is this way, if you're looking at it. But now go behind the clock and watch that hand go, right? It switched directions. What's important is the relative direction of this normal to the surface with what we call the clock, what we started off as a counterclockwise tangent vector. And they remain consistent with Green's theorem because the normal gives rise to k hat, but the tangent gives rise to the counterclockwise tangent here. So it's a relative choice. What does that mean? Well, it means had you done the same surface, and I'm going to draw the same surface over just on the same board. Let's continue here on this board. Had you done this same surface, okay? I have to erase the whole thing because I want to redirect the. So you got this boundary. But now I go this way, T hat. Okay? Because there's no absolute clockwise or counterclockwise in 3 dimensions. You could have been looking from the bottom or the up, or can wiggle all over the place. If I went this way, but the surface still has its correct direction of being in, right? That's still the surface. And there's the surface that I'm making with it. So now I take a piece of the surface, look at it here. Here's the sock. Here are the threads that go in. This is in hat, the unit vector in. This is the tangent hat, the unit vector along the tangent. The prescription is tangent cross in goes to n hat. So in this case, n hat, which is still always going to be tangent cross n hat is pointing this way. N hat would be pointing this way. In other words, if you were to put your foot in it, the first n hat is pointing away from your foot. The second n hat is pointing towards your foot. It doesn't matter because you switch your tangent hat direction. The theorem is going to work. Okay? So that's a little bit of geometry. That's the technical part of all of this that you have to get the whole thing right. Okay? And this is Stokes' theorem. This is Stokes' theorem. So I'm going to do a computation about this in 1 minute. Pardon me. But I want to put one last, yeah, do you have a question? Oh, I thought I saw a hand going up. I'm so excited when I see the possibility of a hand going up. It's like a bidder. $50 right there. 50, 55, anybody? No. Okay, so this is Stokes' theorem. And I mean, this is the big thing right here, okay? Maybe it doesn't feel like a punchline to you, but if you take a look at the last section of the book, which I will not be testing on, but those of you who are interested in thinking mathematically or in thinking about mathematical physics in a more general way, this is the beginning of what's called differential geometry. Okay? This is the beginning of a whole new subject on differential geometry. So this is the jumping off point. And the idea that there are something called forms in differential geometry, and the integral of a one form over a domain is equal to the integral of the function over the boundary. You lose derivatives. This is a very ubiquitous in multiple dimensions also, okay? What else do I want to say? I want to say something, that's for the people who want to go into mathematics or the mathematical aspects of this. I want to say something about the physics of this, because most of you are engineers and you will actually encounter the physics of this more often than not. Okay? So, so the gravitational law and electricity and magnetism they have the property of the following relationships, okay? I'll just do it for the electrical vector, the electrical force, okay? What you have is that if E is the electrical field, the divergence of E is equal to the charge density. Now I'm going to use delta, because delta, this is the divergence of the vector, the electrical vector field is equal to the charge density. Now, those of you who have taken E&M already will say, Professor, no, it's like 4 pi with a E. Don't worry about that, okay? I'm trying to give you this in spirit right here. The point is the derivatives of the force are equal to the source. The derivatives of the force are equal to the source. So too for magnetostatics, the curl of the magnetic field is equal to the current density. So what you want to know is if I set up a source of charges or a source of current, what's the resultant force fields that I'm going to create? So you need a way to solve these equations. That is to say, get B in terms of J. You have to integrate these equations somehow. And that's what Stokes and divergence theorem actually provides you the opportunity to do. Because what do they say? Let me take a look at the electrical field. And the classic example you get all the time is the following. E.g., and I'm going to actually do it, okay? Let me do it. Let delta of x, y, z be a constant charge density sphere. Let delta of x, y, z be a constant charge density sphere, okay? Total charge Q, that's usually used for charge. volume 4 pi r cubed over 3. It's a sphere. What is the electrical field from this? Due to this source. Okay? And this is the way we do it, everybody. This is the way you do it. You take x, y, z, and you put your charge sphere right there. Okay? This is a sphere of radius r. This is a sphere of radius r. Okay? Now, you recognize that Green's theorem is going to help you out here, because Green's theorem is going to let me remove a derivative. So let me remove that derivative right now. Okay? So what am I going to do? I'm going to take, I just erased the thing I need. I'm going to take the equation, the divergence of the electrical field is equal to the charge density delta, and I'm going to put it into, I'm going to integrate both sides of this equation. So I'm going to have the triple integral of the divergence of the electrical field integrated with respect to volume is equal to the triple integral of the charge density integrated with respect to volume. And this is true over any domain. Any domain. Now I get to choose the domain. Okay? Now we need to pause. And the domain we choose is one that is compatible. That sort of makes sense. So we have to use a little of our physical intuition here. This is a spherically symmetric charge, right? It should have a spherically symmetric electrical field. There's no preferred direction in space for seeing that charge, so the electrical field had better not manifest a direction, okay? So what we do is we create, I learned it was called a Gaussian sphere. We learned it was called a Gaussian sphere. What you do is you make this imaginary sphere in your head of arbitrary radius, okay? So let's do that. Let's choose D is an imaginary sphere of arbitrary radius. Okay? So I'm going to use the radius is going to be rho, because that's like the spherical coordinate rho, okay? That's why I didn't use rho for the charge density. So this is spherical coordinate rho, chosen for the spherical coordinate. Okay? So case one, rho is bigger than r. I'm going to put the sphere, I'm going to put this imaginary sphere away from my charge. Okay? But that means the sphere is going to completely surround my charge. So here's my charge, and here's this sphere, and this is radius r, and this is radius rho. Okay? So my domain D is this one. D is the big one, is the imaginary one with the dashed line. Okay? So I have the triple integral of the divergence. I've already lost that. The triple integral of the divergence of E dV is equal to, well, it's the integral of the charge density with respect to volume, right? But I'm taking in all of the volume where the charge is, so that's the total charge. The right-hand side evaluates to the total charge. Okay? So this is the total charge Q. Okay? Now, by the divergence theorem, so I'm going to put a sub-rho here to emphasize that's a radius rho. Just to emphasize that it's associated with rho. By the divergence theorem, the right-hand side is equal to E dot n hat dA. It is the normal component of E on the boundary of this sphere. Normal is radially outward, right? It's the radially outward component. And this is on the boundary of the sphere d rho. And this is Q. Okay? Well, what is this? I said that this should not have any preferred direction. Right? So, but this is a sphere, right? So it's every point in this integration is at the same distance from the origin, and it's just at a different direction. It's a different location. So this should be independent of what you're integrating. This comes out. Right? Directional independence means that this integral doesn't depend, this E dot n hat doesn't depend on your coordinates on this spherical shell. Okay? So this thing comes out. So this is the normal component of the electrical field, which is the radially outward component of the electrical field. If you have a charge, it's radially outward component. Okay? Multiplied by the double integral of dA on the sphere. Well, that's just the area of the sphere, right? Which is 4 pi rho squared. So this thing tells you, and that's equal to Q. So that says the radial component, E dot n hat, is equal to the radial component of electrical field which is equal to the total charge divided by 4 pi rho squared. What do you have to concern yourself with? It's proportional to the total charge that you've encompassed, and it's reciprocal distance squared, 1 over distance squared. That's 1 over distance squared law for Coulomb forces. Okay? It's also the 1 over, if you had replaced this with mass density and the gravitational force, you would have the mass divided by the distance squared, and that's the 1 over r squared distance, the force law for gravitational force. It's the same thing. So that's how it relates to divergence theorem. This is outside the sphere. What happens inside the sphere? We're just going to pause and do this inside the sphere. It's actually very useful. What happens to the electrical field inside the sphere? Well, the left-hand side, everything goes through as you like. It's the same thing, right? The left-hand side, nothing changed. It's the right-hand side that changes. So I have to say that E dot n hat, the radially outward vector field, so this is inside the sphere, E dot n hat times the surface area of each of these shells, 4 pi rho squared, is equal to the integral, the triple integral over the volume of the density, which is a constant density, integrated with respect to the volume. Okay? Well, here you got to use spherical coordinates. So you got to use spherical coordinates. The delta comes out, the density comes out. And if you recall spherical coordinates, this is going to be the integral from 0 to 2 pi, the integral from 0 to pi, the integral from 0 to rho. Right? This is going to be the integral from 0 to 2 pi, 0 to rho of rho squared d rho. Well, it's the volume, right? I mean, we know it's the volume. We know it's the volume. I'm kind of making a big hash of this thing. It's just the volume, right? Are we okay with that? It's just the volume? Yeah, it's just the volume. Rho squared sine phi. Rho squared d rho sine phi d phi d theta. But that's the volume of a sphere of radius rho, which is 4 pi over 3 rho cubed. And the density, what's the density? Well, we've understood this now. The density is the total charge divided by the total volume. Right? The total charge is Q. And the total volume is 4 pi r cubed over 3. Okay? So you see that the 4 pi over 3 cancels out on the right-hand side. And you're left with E dot n hat is equal to, let's see what we get. We've got the Q again. We've got a 4 pi rho squared on the left-hand side, which we have to divide. So we lose 2 powers of rho on the right-hand side. So we're going to have rho over 4 pi r. Is that correct? Sorry, rho. I got to get my, I want to put my 4 pi's in the right place. And then we have an r squared over here. There you go. So what's this? All I did was I canceled the 4 pi over 3, the 4 pi over 3. I got rho cubed over r cubed over 4 pi r squared. So rho cubed over rho squared is rho. I still get an r cubed, and I get the 4 pi. I just factored it out in a certain way. Okay? So look what happens. If I were to plot the radial component of the electrical field, E dot n hat, which is the radial component, as a function of rho, what we see, and I should bring this down a little bit so you can see it better, rho and E, the vector field goes as 1 over rho squared for rho greater than r, and then it goes linearly in rho for rho less than r. So the force goes linearly in distance, the electrical field goes linearly as a linear function of distance from the center when you're inside this sphere, and then it decays as 1 over r, or rho squared, as you go outside the sphere. And of course, they meet. At rho equals r, those two expressions are equal to one another. So this is how you use the divergence theorem. I'll use the Stokes theorem next time. I want to point out to you there's something fun about this. This is the same thing as this is the same thing that would happen with the mass of the Earth, the mass and the radius of the Earth. And so if you were to dig a shaft right through the center of the Earth and jump through it, you would have a linear force law, which means you would actually behave as the same way as spring oscillates. You would have constant frequency oscillations. So you would just kind of go through the Earth, come to the other side, come bouncing back, and come bouncing through. And your maximum speed would be at the center, just like if you were watching a spring oscillate. Okay?